Xudong. I'm from the University of Bristol. Today I'm going to present my paper regarding partial modality translation based on diffusion models for prostate MR and ultrasound image registration. In the diagnosis of prostate cancer, the urologist needs to use the MRI to identify the suspicious areas visible only in MRI to guide the ultrasound biopsy targeting on those suspicious areas to confirm the diagnosis. So aligning MR and ultrasound images is essential and currently performed mainly by high-skilled experts due to the significant difference between the modalities, which also pose challenges for AI algorithms. So in this paper, we combine 3D diffusion models and GANs to translate both MR and ultrasound images to an intermediate pseudo modality, reducing the modality difference between these images and easier the automatic registration process. So here is our network structure. As you can see, we have the original image and the translated image. We use the optimal transport concept, which means that if we construct a scheduler bridge between the original image and the target image, we're going to have many middle status inside this scheduler bridge. And we assume that our network could translate any middle status in the scheduler bridge to the target domain. And if we have the original input image x0 and the target image x1, we could get any intermediate status inside this scheduler bridge. So every time when we have an input image, we randomly select one t from the scheduler bridge, which make it at the middle status in the scheduler bridge, which is definitely an interpolation between this original image and target image and the Gaussian noise. So it's a diffusion process. So we call this middle status in the scheduler bridge as a noisy version of the input image. So we apply this noisy version of the input image to at the input of the network, translate this one to a target domain. So as for the loss function, we apply a scheduler bridge loss, which constrains the translation from the initial distribution to the target distribution to achieve optimal transport. And we also have a discriminator loss, which differentiates between the original image and the result image. And we also have the adversary loss, which could fight with the discriminator to make the generated result on both sides appears as authentic as possible. And we also introduce texture loss. Here we assume that the shallow layer of the latent space features will harvest the texture information of the images. As we want the texture information of the images to be similar in the pseudo middle modality, so we add a loss between this shallow layer latent space features. And also we have a regularization loss, which could ensure the content of the results and the original image to be similar. So yeah, the existing modality translation method could be divided to GAN-based method and diffusion model-based method, and both of them are fully modality translation from one modality to another. We choose one method from both sides at the baseline method. This is the result of using a GAN-based method from translate MR to ultrasound. As we can see, the fake ultrasound, which is noisy, which is almost useless in the registration process. So we could just ignore this result in the following comparison. And here we have the result. And this is the original MR from 2 patients. This is the original ultrasound from 2 patients. This is the result using a state-of-art diffusion model-based method from MR to ultrasound. The target is to register MR to ultrasound. So we translate MR to ultrasound using the baseline method because it's a fully translation method. As our method, we have partial translation method, which means we translate MR and ultrasound to middle modalities. So as we can see, our result looks quite similar. They looks like a single modality, and this two, the original MR and ultrasound, is easy to be distinct, but here, visually, and if we look at here, this result using a diffusion model-based method, this two looks also very different. Yes, we also use some numerical result to prove our result is better than the baseline method, which is the FID and KID, which could evaluate the distance between two distributions. As we can see, the original FID between the MR and ultrasound images almost 500. The baseline method decreases this number by more than 15%, but our method decreases more than 30%, which is even over double of the baseline method. As for the KID, our method decreased the original score by over 3 times of the baseline method. So, which means that our method could create result which have similar or closer modality distance. Yeah, we also apply a mutual information-based method to do the registration on the original MR and ultrasound and the translated result both of our method and the baseline method. As we can see here, this is a prostate boundary of the MR image. This is from another patient, and this is the baseline, the boundary of the MR in the ultrasound image. As we can see here, the registration result using the original MR and ultrasound. As we can see, the boundaries are quite different, which means that the registration accuracy is very low. And if we use the translated result using the diffusion model-based baseline method, we can see the result is also very bad. It's easy to distinguish the boundary of the two images here and here. As for our method, we can see here, this is the one boundary, this is the second boundary. They're quite close here. And also, if we look at this image, it's almost impossible to distinguish them, which means that our method could make the registration easier and higher accuracy. So to make a conclusion, we are the first to achieve such unsupervised registration between 3D MR and ultrasound images through this modality translation concept. And this is quite different with the existing registration method, which heavily rely on the segmentation, which require a large amount of label data. And also, we are the first to use this idea of a partial modality translation between MR and ultrasound images, so as to easier the translation problem, as fully translation from one modality to another is harder than the partial modality translation. Also, our registration result is better.